Have you watched any of these video tutorials for integration?
Um, not yet.
Okay, well let's watch one, and the
Okay.
one that I'm going to show you is the one that addresses your question.
Okay.
Okay. Now, by the way, um, what do you have a tablet or a phone or anything like
Yep.
that? Yep. Do you use Android or Apple?
Android.
Android? Okay.
Yep.
So the app for this is available on Google Play,
Mhm.
or if you prefer Mac, it's available on the Apple Store as well. Okay. Use the
Okay.
same login as what you use on the computer,
Mhm.
and you can basically watch it on your phone or whatever. It'll be easier for you to watch than having to organize to sit in front of a computer or a desktop.
So
Okay.
what's it called?
Just
Like,
Sky Academy,
okay.
but I think it's one word.
All right.
Okay. So let me know when you're ready,
Yep.
and we'll
Ready.
watch it. We'll watch it in 1.5 times the speed because sometimes I talk slow.
Hi, this is Saul, and I'm the Principal and Director of Sky Academy. And in this episode, what I want to do is build on our knowledge of integration. And in the last episode, what we did was we looked at the relationship between integration and the area under a curve, especially if the curve falls below the x-axis, right? Now what I want to do is look at the area between two curves, right? So this area here. So if you have two curves, one curve being f of x, the other curve being g of x, how do you find the area between them? Okay. Well, let me put it to you this way. If you know what their 2 points of intersection are, so let's say the x-coordinates of their point of intersection is at A and B, right? The area between them, right? Let me show you diagrammatically, right? This area, which is black, is going to be equal to the area which is red minus the area which is blue. You see that? So this area which is black is actually the area of the top curve, the area that the top curve makes with the x-axis, minus the area that the bottom curve makes with the x-axis. So if you took this part out of this part of the graph, what you'd be left with is this bit here. Do you see how that works? Yeah. So basically, as long as you've got the same limits, right? So from A to B, basically what you have is the integral of the top curve minus the integral of the bottom curve. The area bounded by the top curve and the x-axis minus the integral bounded by the bottom curve and the x-axis. Does that make sense? Cool. So, basically, the area between two curves is given by f of x between A and B minus g of x between A and B. Okay. Now, let me just say something at this point here. You're not always going to be given A and B, the limits. You're not always going to be given the limits on the graph. Okay. Sometimes you have to work out what the limits are. How would you work out where this point is and where this point is? Well, to work out the limits, you basically have to solve the simultaneous equation between these two curves, right? So you work those out using simultaneous equations, right? And that will give you the point that's common to both, where they both intersect, okay? And those points, the x-coordinates of those points are the limits of the area between the two curves. Does that make sense? The other thing that I want to mention is it does not matter. See how in these two curves, they're both above the x-axis? I want you to have a think about it. If one of these curves was below the x-axis or dipped below the x-axis at any point, would that affect the way that we work out the curve? Have a think about it. Right? If you think hard enough, you will realise that it doesn't matter whether either of these curves go above or below the x-axis. Right? To work out the area between those two curves, you simply subtract the integral of the top graph minus the integral of the bottom graph. Does that make sense? So it really doesn't make a difference. Okay. Now, the other thing that I want to mention is this note, right? And this is how I'm going to put it. The difference between the integrals is actually equal to the integral of the differences between the two functions, right? So the difference between the integrals is actually equal to the integral of the differences between the two functions. So what that means is you can subtract one function subtract the top function from the bottom function first, and then integrate, it'll be a whole lot simpler. Alright? So let's have a look at a specific example, because I want to go through this example with you. Okay? And it'll involve us graphing the two curves. And let me stress, I can't stress this enough, if you are given two curves, or if you are given two functions, and they're not sketched for you, please sketch them, so that you have an idea, number one, where they intersect, so where your limits are, and also which curve is above and which curve is below, okay? And just so that you get an overall feel for it, just get used to graphing everything that you, all the information that you're given, just get used to graphing it, okay? It will do you an enormous amount of good in the 2-unit paper when you eventually have to set it, okay? So let's go.
There we go. Does that make sense?
Yeah.
Yeah. So do you understand why we subtract the two now?
Yeah, I think so.
Okay. So the reason why you subtract them is ultimately it's the area of the top curve minus the area of the bottom curve is because you'll have a top area and a bottom area, and you take them away, it leaves the area in between them. Got it?
Yeah.
Yeah. Good.
So the next one is studying volume.
Oh, yes. Volumes of solids, of revolutions.
Yeah.
Yep. Have you started that?
No.
Okay. So you want me to go through it?
Yeah.
All right. All right. Again, we'll watch it at 1.5. That's not too fast for you, is it? 1.5?
It was a little fast.
Do you want me to slow it down?
Yeah.
Okay. All right. I'll play it at 1.5, and if there's things you want me to slow down about it, we'll slow it down.
Okay.
Hi, this is Saul, and I'm the principal and director of Skype Rc, and we've been doing, up until now, a whole series of episodes on integration. And we've come to a point in the topic of integration, which is one of my favourite parts of integration, and that is finding not just the area under a curve, but a volume of a solid shape when a curve is rotated around either the x-axis or the y-axis. Right? In this case, in this episode, we're going to look at a curve being rotated around the x-axis. But in order to do this, I want to actually take you back to finding the area of a circle. Now, the area of a circle is equal to pi r squared. Does that make sense? The area of a circle is pi r squared. Now, the area of a cylinder or a disc, right, is actually pi r squared, which is the circular bit, times the thickness of the circle, which is h. Does that make sense? Right. So the area of the circle is pi r squared. The volume of a cylinder or a volume of a disc, right, is pi r squared h. And we're going to rely on that when we look at the volume of a revolution, volume of a solid of a revolution.
So, Rebecca, are you following that so far?
Yeah.
Okay.
Okay. Cool. So let me go through what I mean by all of this. What is the volume of a solid revolution? Okay. So basically, let's now consider a function y is equal to f of x as it is rotated about the x-axis between x equals to a and x equals to b. So if you've got a curve, y is equal to f of x, say that's your curve in blue, and you're looking at the area between a and b, then the integral of that would just be, the area would just be the integral between a and b, right? And that will give you the area under the curve. But what we're interested in is the volume that would result if we rotated that curve around the x-axis, right?
Does that make sense?
Yeah.
Yeah. Let me show you what I mean. Where is it? So that area there, see that area there?
Yeah.
Right? See how it's kind of like a trapezium, but instead of being have a flat bit, it's like a curvy bit.
Yeah.
If we rotate that around the x-axis, so this bit here. Alright, so this bit here, do you see that bit?
Yeah.
Whoops. If we rotated it, whoops. We rotated that around the x-axis, so kind of rotate it that way. Can you see we have like that, kind of like a leg of ham? You see that? We get that leg of ham type shape.
Okay.
Do you see what I'm talking about? We get that pottery, that it's kind of like a pot on its side. You see that?
Yeah.
When we rotate it?
Yeah.
Yeah. That's what we're looking for. We're trying to find the volume of that. Okay? We're trying to find the volume of this blue bit. We're trying to find the volume of that whole pot. You see what I'm talking about? And that's the center of the it. Yep. It's kind of like rotating a doner kebab, like a a thing of meat on a doner kebab thing.
Yeah.
Yeah. On its side.
Okay.
Yep. That's what we're looking for.
And here it kind of looks like a pot on its side, or a vase on its side. Okay. And can you see the shape of what I'm trying to establish? You've got this curve being rotated around the x-axis. Yes? So I'll just show you what I mean. Basically, we're doing that to the curve. Right? We're rotating it around, and we're trying to create a solid. Okay. Now, this gets pretty complicated, right? There's a lot of, if we were to do it properly, there would be a lot of algebra involved, but I'm going to spare you the algebra and give you just the basic principle of how to work out that volume. Okay, cool. So to work out that volume, we're going to slice up this volume into little mini discs, right? The more discs, the better. And the thinner the discs, the better. Okay? So what we're going to be doing is we're going to slice it up into little mini discs. Now, what I want to do is work out the area of one of the discs. Let's take any area whatsoever. And I've just done that here. You see that? So that's a disc, right? The thickness of that disc we're going to call dx. Right? dx meaning an increment of x. dx. Not only that, but the radius of that disc will be determined by the function, right? By the equation of the function. But it'll be the equation of the function at that value of x. Does that make sense? So basically what I've got is that the radius is equal to f of x. So the volume of that disk is going to be pi of that function squared times
Here we go.
the dx, which is the thickness. Right?
Hang on, let me
And
go
I
back
want
to
you
that.
see how that of that function squared times.
There we go. So what I want you to see is that the area of this, the volume of this disk will be, like the volume of any disk, pi r squared, h. Does that make sense? Now, what I want you to see is that the radius of this disk, right, will be given by the function at any time, which is f of x. Okay? It's the y coordinate. It's the y coordinate. At whatever the x coordinate is, it's whatever the y coordinate is, right? Put into the function, right? So if x is equal to 2, the radius will be f of 2. Does that make sense?
Yeah.
Yeah. So it's the volume would be pi times f of x squared, and the thickness of this disk will be really, really tiny, right?
Yeah.
The thickness, which is your height of the cylinder, is going to be some really, really, really small, well, that's what the D stands for, really, really small slice of x. Okay? Really small width of x. Got it?
Yeah.
Yeah. So what I want you to know is that it's pi f of x squared dx. Okay? But here's the other thing I want you to know. Basically, to find the volume of the pot, of the volume of the solid, you've got to add up all the little infinite little mini disks all together.
Okay.
dx, which is the bigness, right? And I want you to see how that emulates, I'll come around this side, how it emulates that formula there. See, so you got the pi here, you've got the r squared here, and you've got the h there. And that gives you the volume of a disk. Does that make sense? Alright. Now, to find the area between, so to find the volume between A and B, we're going to divide this up into a whole series of little disks between A and B and find the volume of each of those disks and add them all up. Does that make sense? Right? And so the volume would be equal to the sum, the integral sign means sum, from A to B of pi f of x squared dx. Right? Now, if I were to prove that, it would require a whole lot of algebra, so I'm going to spare you the algebra and spare you all the theory, but I just want you to know that the volume of a solid of revolution, okay, of a curve f of x will take on this form. Pi times the function squared dx. Right? So I'm going to put a big, massive box around that, and I want you to know that that is the formula of the volume of a solid revolution. In the next episode, I will be going through a specific example with you. Okay. So for the time being, just know that that is the formula. Thank you very much for watching.
Okay, so it's exercise 3.9, page 154, which is what you were talking about. Yep, cool. Got it? All right, so let's do an example, shall we?
Yep.
Okay, you'll get the idea. It's really simple. It's not hard. The theory behind it can be a little bit tricky, but doing the questions isn't really that hard. Okay? Doing the questions isn't that hard. I might even do it 1.5 times the speed because you'll get the gist of it fairly soon. You will. It's not that hard.
Hi, this is Saul, and I'm the Principal and Director of Sky Academy. And in the last episode, what we did was we looked at volumes of solids of revolution. And I gave you the theory on basically what it is. It's when you take a curve and you rotate that curve around the x-axis, and you are looking at the volume that's created by doing that, by rotating the curve around the x-axis. Right? And we came up with a specific formula that resembled the formula to find the volume of a disc or a cylinder. Do you remember that? Okay. Now, the formula that we came up with, right, this is basically the formula in a nutshell. The volume is equal to pi times the integral from a to b of the square of the function dx. Okay. So, I'll show you how to do specific examples like this, but this is basically the formula for the volume of a solid of revolution made by rotating that function about the x-axis between x is equal to a and x is equal to b. Right? Good. So let's have a look at a specific example. Right? If we launch into a specific example, it might make things a little bit clearer. Right? So here we go. Find the volume of a solid revolution formed when y is equal to x cubed. So we've got the function, the graph of y is equal to x cubed is rotated about the x-axis between 0 and 2. Okay? So you see, I've actually done the work in advance. And so what we want is the function between 0 and 2, 0 here and 2 here, rotated around the x-axis. So it's going to look like the bell of a trumpet. Okay, do you see that? And what we're going to...
Now, Rebecca,
Yeah.
if there's anything that you want me to slow down or repeat or go back, let me know, okay?
Okay.
do, so we're going to find the volume of that using this formula. Okay? So the volume is going to be pi times the integral work that out. That gives us pi times the integral 0 to 2. X cubed squared is x to the power of 6 dx, right? Which gives us pi lots of x to the power of 7 on 7 when we integrate it. So when we integrate x to the power of 6, we get x to the power of 7 on 7, right? Between 2 and 0. Does that make sense? That's going to give us pi lots of 2 to the power of 7 over 7 minus 0 to the power of 7 over 7. Which gives us what's 2 to the power of 7. Alright, so let's work this out. 2 to the power of 3 is 8. 2 to the power of 4 is 16. 8 times 16, 64 double 64, 128. So basically, the volume is going to be 128 pi on 7 units, cubic units. Does that make sense? Do you understand what you follow what we've just done here? Right? This is basically the way that we find the volume of the volume of a solid revolution. Okay.
Does that make sense?
Yeah, but like, what if you can't draw the diagram?
Then draw the diagram.
Uh,
Yeah, it helps. It really helps to draw the graph. And if you can't draw the solid, don't worry about drawing the solid.
okay.
Yep. But at least draw the two-dimensional graph that needs to be rotated. Does that make sense?
Yeah.
But in terms of finding the volume, how is it different from finding the area? What do we have to do that's different?
Add the pi.
Add the pi, or multiply by
square.
pi. Yep. And then
And, like,
square
square
the
the
function before you integrate.
Yeah.
Is that any harder than what you're used to? Not that much more, is it?
Yeah.
Not that much harder, is it?
No.
Alright, that's all you have to do. To find the volume, you just square the function and multiply by pi, and then integrate as usual. Got it?
Yeah.
I'm going to do an example that's slightly different. So let's have a look at this one. So this next example is about rotating around the y-axis as opposed to the x-axis. Okay? Alright, let's have a look at this.
Let's have a look at this example, because this example is slightly different. What this example takes into consideration is that we are now rotating the function about the y-axis, not the x-axis. Okay? So what we're doing is we're considering rotations about the y-axis. So let's read it out. Find the volume when x equals, so y equals to x squared is rotated about the y-axis between y is equal to 1 and y is equal to 4. Okay? So to do this sort of question, the first thing we have to do, remember, when we're rotating about the y-axis, is make the function change the subject of the formula. So we need to make the function expressed in terms of x as opposed to in terms of y. So let's do that first, and I'll do this over here. So y equals to x squared becomes x squared equals to y, x equals to square root of y, right? And is it positive or negative? Well, we're rotating the positive, this arm, about the y-axis. So let's make that positive, even though there will be both the positive arm and the negative arm. Okay? But we're rotating the positive arm around the y-axis. So let's use the positive. Okay? And in fact, I will probably label it like this, like a power of half. Okay? So let's work this out. So the volume of revolution is equal to pi times the integral, and in this case it's the integral from 1 to 4. So the limits have already been given to us in terms of y. Right? So if the limits were given to us in terms of x instead, we would have to convert it to the y. Okay? So limits in terms of y. Right? So here we go. Pi times the integral from 1 to 4 of the function, which is y to the power of half, y to the power of half, all squared, and this time, because we're rotating around the y-axis, we're integrating with respect to y. Okay? So all of that would equal pi 1, 4, y to the power of half to the power of 2 is just y to the power of 1, see y, which gives you pi times y squared on 2. Let's work that out. Pi 4 squared on 2 minus 1 squared on 2 gives you pi 16 on 2 minus 1 2 gives you 15 pi sense? So hopefully you can follow the algebra, but the key to notice with these sort of questions, when you're doing volumes of solids of revolution, is that you need to square the function, right? Just like we squared the function there, and we squared the function there, right? And when you're doing volumes of solids of revolution rotating around the y-axis, the other thing to remember is you need to express that function, making x a subject of the formula in terms of y, like we did here, and also change the limits and integrate with respect to y as well.
Now, Rebecca,
Yeah.
does that make sense?
Yeah.
So when you're doing it rotating around the y-axis instead of the x-axis, you got to make the function in terms of x. Sorry, x is subject to the formula in terms of y, and then square x, right?
Yeah.
Now, how would that translate with the limits? So what are the limits here? What would the limits here be? X equals 2, so y equals to 1, y equals to 4, which is what we used, right? But sometimes the questions might give us the limits in terms of x instead. So what would the limits be in terms of x in this question?
2.
Here?
Yep.
Yep. 2 and?
1.
Yeah. Got it?
Yeah.
Yeah. 1 and 2. So if the question was given to us as you would then have to put that into the equation and get your 1 and your 4 to put there and there. Does that make sense?
But like if the limits were
Already.
1 and 2, couldn't you have just used like x squared?
Yes, that's right. So you put 1 into there and make it x squared, and 2 into there, make it 4. Yeah, that's right. Yeah, and oh yes, the way some teachers will teach it, because we ultimately want x squared. They will say if you've already given if the function's already given to you as x squared, just put y there. So basically all it is v equals to pi, y equals to a, y equals to b, for x squared dy. So whatever that is, they'll just put that in. See how y squared is equal to y? So x squared is equal to y? Some teachers will say don't square root and then square it again. Just use the x squared value. So y dy. Yeah. Yeah. And either's fine. If you understand the theory, I would just put that in to there instead of square rooting and then squaring it. Got it?
Yeah.
Alright. So now that we've done the theory and a couple of examples, if we go back to the questions that you have, which ones are they?
I just start from the beginning.
Mm-hmm.
Yeah.
Yeah. Let's start with an easy one. Let's start with the first one. Just, oh no, we've already done. Let's have a look. Do the second question.
Okay. So I should always like draw the diagram, right?
Yeah. Where you can, I would.
Okay.
So it doesn't have to be the most beautiful diagram, as I've truly demonstrated.
Oh, so you don't times the pi, right? You
No.
just leave it.
Yeah, leave it out the front.
Okay. I don't know if I got this right, but I got 291.66 or 67 pi.
Hang on. Let me work it out.
Okay.
Okay. Is that what you got? What I've got?
Oh, jokes. Oh, okay. Because you know how it's like x plus 1 squared.
Yep.
I did x plus 1 cube over 3.
Oh, okay. Yeah, I know. I see what you did. Yeah. But do you see how you're supposed to, if you expand it and then integrate?
Yep.
Yeah. After 2, try 3.
100, is it 161.67?
Could be. I think that sounds right. Let me work that out. So what'd you get?
Oh, that's okay.
What'd you get?
161.67.
Point. Yeah, let's have a look.
Uh,
Are you right or am I right? Or are we both wrong?
I'll have a look.
Oh, I know. Hang on. I know. You're right. I'll tell you why. Yep. Good. You're right. Okay. Rebecca,
Yes?
you're correct.
Oh, yes.
All right. Okay. All right. So what I want you to do is try question 3.
I got 376 pi over 15.
That could be right. So you should get x to the power of 4 plus 4x squared plus 4 dx between 0 and 2 already. I like the way your answer's sounding. The fact that you've got an answer over 15 is a good sign.
Okay.
Yeah, I think you're right. 2 to the power of 5, 32 over
Yeah.
5. 2 to the power of 3 is 8, 32 over 3 plus 8 minus 0. Okay, so you should have 3 times 32 is 96 plus 160 plus 120 over 15 pi. So what'd you get? 280, 376 over 15 pi. Yep, that's correct. Beautiful. Got it?
Yes.
Cool.